Hello, welcome to today's physics practical demonstration. In this section, we'll conduct an experiment using a concave mirror to explore the relationship between the object distance and the image distance. I'll be your tutor today and I'll guide you through measuring and recording your data, constructing your table of results from your recorded data, using your table of results to plot your graph, and finally determine your slope from your plotted graph. This will deepen your understanding in key concepts like magnification and focal length. Before starting up our experiment, let's review some apparatus we will need. You need a ray box as your light source, your concave mirror as your reflector, your mirror holder to hold your mirror in its position, then your screen to capture the reflected image from the ray box, and other necessary apparatus like the meter rule for measurements. Now let's mount up the apparatus as shown in the figure above. In the figure above, we have our ray box in this position facing the concave mirror while the screen is in opposite direction to the concave mirror. Over here, from the ray box or our light source to the mirror is our object distance, and from the mirror to the screen is our image distance. We are to set our object distance to 25 centimeters. So from this place to where the lens is, I'll set it to 25 as our object distance. Now I'm done with the object distance. I will light up my light source for the light source to project its rays on the concave mirror, of which it will reflect it to the screen, and the screen will capture our reflected image. We are to measure and record our distance from the mirror to the screen as the image distance. So over here, I'll take up my rule and measure the distance from this place to this place. But before doing that, we need to adjust the screen until a clear image of this cross-section wire of the ray box is found on the screen. So you adjust the screen up to this place is a blur image. We want a sharp image, so we will continue to adjust it until a clear image as such is found on the screen. So since we have our clear image, so we take a rule and measure the distance from the screen to our reflected mirror. The image distance to be 34. So let's construct our table of results first. Our u as the object distance per centimeter, that's the SI unit for u. Then we are to record v also per centimeters, that's the image distance, and we are starting with 25.0 centimeters. For 25.0 centimeters, we had 34.0 centimeters as our image distance. We now proceed with different values of u, such as 30, 35, 40, 45 upwards. So for 40, or for 30 rather, for 30 we set our object distance to 30 centimeters. So 30 centimeters. So now I've set the object distance to 30 centimeters. Then I adjust the screen until a clear image is formed again. This is a blur image. Clear image is forming, yes, and this is a clear image. If you bring it closer, another blur image will be formed again. So it means our clear image is at this point. Then from here, we record our image distance. Over here, we have 28.0 to be our image distance. When U is 30.0 centimeters, we have 28.0 centimeters. This shows that as the object distance increases, the image distance does decrease. Let's confirm if it follows that same trend. We now set our object distance to 35. We have set our object distance to 35. Over here, 35.0. Now we adjust the screen until a clear image is formed. Over here, we have a clear image at this place. We take our meter rule and record the value of our V. From here, we have 25.5 centimeters. So our V is 25.5 centimeters. Now we proceed with U, 40 and 45. We now start with U, 40 centimeters. We'll take our rule and measure U, 40 centimeters. So from here to here is 40 centimeters. Then we adjust the screen again until another clear image is formed on the screen. And this is a clear image. We take our rule and measure the distance of V. Over here we have 24.6 centimeters. So 24.6 centimeters. So it's following the same trend. As the object distance increases, the image distance decreases. That's the trend. We proceed with our last value, which is 45. We set our U, the object distance, to 45. We adjust our screen again until a clear image is formed. And over here, there is a clear image, as you can see. Then we record our value for V, the image distance. Over here we have 22.8 centimeters. So 22.8 centimeters. Now we are done taking our recordings from this experiment. We proceed with the question again, which says we should evaluate P such that P is equal to U on V. So in doing that, I'll take my calculator and I hope you also take yours as we go along with it. 25 on 34, 0.735. Over here, we have about 10 decimal values or 10 decimal values on my calculator, but we are only interested in 3 decimal values. Now you should leave your division. That's whenever you divide anything in physics practical, you should leave it to at least 3 decimal place. When you are recording your raw data, you should leave it to at least 1 decimal place. When it's multiplication, you can leave it to at least 2 decimal place. But bear in mind that when it's division, it must be at least 3 decimal place. Now we are done with our evaluation. We head on to the questions, which says we should plot a graph of P on the vertical axis and V on the horizontal axis. Before plotting the graph, you need to calculate and choose a reasonable scale for your graph. In physics practical way, our reasonable scale is 1, 2, and 5. 1, 2, and 5. And decimals of it, you can have 0.001. Supposing you have 1 in it, is a reasonable scale. You can have 0.2, it's a reasonable scale. You can have 0.05 times 10 raised to the power negative 8 is a reasonable scale. Supposing you have 1, 2, and 5 in it. And you can also have it in tens and hundreds, such as you can have 100, 100, you can have 20, you can have 5,000. Supposing you have 1, 2, and 5 in it, it's a reasonable scale. Now, when you come in choosing your scale, we have 2 procedures. First procedure, you take your maximum value, then you divide it by the number of boxes you have. Number of boxes. So if you are working on the vertical axis, we have 10 boxes at that place. If you are working on this axis, it's 12 boxes. And you are working on the horizontal axis, that one is 10 boxes. So for this one, we are to plot a graph of P on the vertical axis. So over here is our P against V on the horizontal axis. So V per centimeters. Correct distinguishing of axes, we award marks on it. Then we come to choosing our reasonable scale. Let's start with the horizontal axis. Over here, our maximum value is 34.0. We take 34.0, 34 divided by 10 boxes. So we are working with 10 boxes. That's on the horizontal axis. We just have 10 boxes. And when you divide, you come and have 3.4 as your scale. 3.4 as your scale. But because 3.4 is not a reasonable scale, we run it up to the nearest reasonable scale. Always we run it upward. So from 3, our nearest reasonable scale is 5. So we run our scale to 5.0. So it means that we can take 5.0. If you are starting both axes from 0, we can have 5, 10, 15, 20, 25, 30, 35 are upwards. The interval between these values is what? 5. That's what we have over this place. And the second procedure is you take the difference between